Yeah. Okay, so now the matrix representation of this linear operator relative to the basis. Okay, relative to the basis would be T1. Okay, and so this is 2 minus 4, 2 plus 4t, and 1 minus t, b. Okay, and the b coordinate of this polynomial is 2 and 4 here, and the b coordinate of the polynomial 1 minus t is 1 minus 1. Okay, right? So this one is the matrix representation of T relative to the basis for P1. Okay, so we have this one. Right? Now we consider another basis. We call C, and it consists of 2 polynomials in P1. Okay? Now, we look at the image of the first basis vector in C. Okay, and so by the linearity, okay, so from the specification here, this is just the sum of T1 and T2, and we find that this is actually once again, this is 3, 1 plus t. Okay, so it's just the 3 times the 1 plus t, the same 1 plus t here. Okay, so we just write it plus 0, 1 minus 4t. Because later on we will need this linear combination, and t of 1 minus 4t is t1 minus 4 tt, and the result again is minus 1 minus 2 1 minus 4t, so it's 0 1 plus t plus minus 2 1 minus 4t. Okay, so now the matrix representation of T relative to the new basis C here, it's okay. So now we check the C coordinate of the image of these 2 basis vectors in C. Okay, and from here, that we already read it as a linear combination of the basis vector in C. So this goes to this saying that it's 3, 0. And this implies that it's equal to 0 minus 2. So we have 3, 0, 0 minus 2. Now, if you compare these 2 matrices, this matrix is diagonal matrix. Okay, but this this matrix representation is not diagonal matrix. Okay. And we usually consider diagonal matrix are simple matrices. Okay. Okay. Now with this one, now note that for any polynomial in P1 with the C coordinate to be A1, A2, that means that, so if we know the C coordinate of PT to be A1, A2, we can recover the polynomial by using the coordinate vector. So this is A1, E1 plus T, plus A2, 1 minus 4T. Okay, so PT is actually this polynomial. Okay, with that, then we have immediately the T, PT. Okay, so the TPT now, because T is A1, 1 minus T, 1 plus T, plus A2, 1 minus 4T, and this is A1, T, 1 plus T, plus A2, T, 1 minus 4T. Okay, and this is 3 times A1, 1 plus T, because T of 1 plus T is 3 times 1 plus T. Okay, and T of 1 minus 4T is minus 2 times 1 minus 4T. Okay, so we can write down immediately, because T of 1 plus T is 3 times 1 plus T, and here we have A2 of 1 minus 4T. Okay. So a diagonal matrix representation facilitates our computation of the transformation of the images. Okay. So now we have a general problem. Okay, so the general question is that given a linear operator right, where the V is n-dimensional. Okay, so given a linear operator on an n-dimensional vector space, can we find a basis C for V such that the matrix representation of T relative to the basis C is diagonal? Okay, so that is the general questions for that. Any questions on this question? Okay. No? Good. Now this question is equivalent to asking for a basis C, V1, V2 up to Vn. Right? So you are asking for a basis for V such that you need the Vi equal to lambda I, Vi for all I. Okay? So this is equivalent to saying that. So you require the image of each basis, each vector in the basis is equal to a multiple of the same basis vector Vi. Okay? So you are saying that just like in here, okay, 3 it's obtained because here, and minus 2 is obtained minus 2 here. Right? And the reason is that T Vi C is equal to lambda I Ei. Okay? So the column vector, the i's, because TVI C, so this is equal to, so this is actually okay. So the ith column corresponding to this column vector, but the ith column vector, ith column is just lambda I times Ei. Okay, it's Ei here. All right. So to have a diagonal matrix representation, if and only if that the ith column of this matrix representation is equal to lambda I times the standard unit vector Ei. But this is if and only if, okay. But what is Ei? Ei is just Vi relative to C, right? So for this, the ith vector in the basis, its C coordinate, okay? Its C coordinate is just equal to the Ei. Any questions? Okay, say for example V1 is V1 1 0 V2 is 0 Okay, so V1 has a unique representation as a linear combination of the vectors in the same basis here. So V1 is 1 times V1 plus 0 V2, sorry, plus 0 Vn. V2 is 0 V1 plus 1 V2, etc. Up to 0 Vn. And the Vn is 0 V1 plus 0 V2 plus 1 Vn. So that V1 C is just 1, is the 1 0 0, which is E1. V2 0 1, so this is E2. Vn En. Okay? All right. So the EI is just C coordinate of VI. But C coordinate is linear, so this is C, right? We can because the C coordinate function is a linear isomorphism. Okay, so you can move the number I inside it. Oh, I'm sorry, I forgot I here. So you get TVI C coordinate equal to lambda IVI C coordinate. And the C coordinate is isomorphism, so it's 1 to 1 and until. So this is saying that TVI should be equal to lambda IVI. Okay. It's a simple proof, okay, to show why this is equal. Okay, so the discussion here, because I use the coordinate, I use the metric representation a lot. So you should be familiar with all the materials in chapter 5. Otherwise, you can't understand the material in chapter 6. Questions? Okay, so that to answer the question here means that to have diagrammatic representation relative to a certain basis is equivalent to asking for a basis and all these vector in the basis satisfying this equation here. Okay, so now we define. So again, for convention, we use F to denote R or C. Okay. Okay. So if the result applies for R or C, then sometimes I just don't mention the scalars. But if a result is good specific for a real case, then I have to explicitly state that it is related to a real case, or the contrary related to the complex case. You will see that they make difference, okay, in our consideration of the eigensystems. Okay, so so the definition, right? So T is an operator, linear operator from B to B. Okay, so, not necessary. I will say later. A linear operator on a vector space. right? So this definition is good for arbitrary linear operator on arbitrary vector spaces. Okay, not necessary. The vector space not necessarily finite dimensional. Okay, just any vector space, and over F. Okay, so the vector space V is over a scale field. So F can be R or C. Now, a scalar lambda in F and a non-zero vector V in the vector space V satisfying the Eigen equation of T. The Eigen equation of T is called this one. Okay. So such they are called Eigen equation. So I will call them as the Eigen equation of T. Right? So if we have a scalar lambda in the F and a non-zero, so we have to emphasize a non-zero vector V. Why? Because if V is zero vector, then zero vector always satisfies this Eigen equation, right? For any lambda. 0, 0, of course. Because for a linear transformation, the image of zero vector goes to zero vector. Okay, so the image of zero vector is zero vector anyway. So that this is automatically true if V is zero vector. So we require the V to be non-zero. Okay. Right, satisfying the Eigen equation. So if we have, so they are called an Eigen value of T and an Eigen vector of T associated with eigenvalue lambda respectively. Okay, so eigenvector must be non-zero. Okay, it must be non-zero, and eigenvector must be associated with an eigenvalue. Okay, so eigenvector cannot exist independent of eigenvalue. Okay, cannot. Okay, so that is the definition. But we have to develop means to solve the problem, right? We have to develop some computational method to solve this Eigen equation. How can we do so? Okay, so now, to solve the Eigen equation, okay, we call this 6.1. Of a linear operator, okay, on an n-dimensional vector space. Okay. if the vector space is not finite dimensional, then the problem is difficult. I have to say so. All right? But now, in this course, we will consider only the case that the vector space V is n-dimensional. In this case, then we do have efficient method to solve the Eigen equation. Okay, so we have n-dimensional vector space. Okay, so to solve it, so we select a basis for V. Okay, and consider the matrix representation of T relative to the basis B. Right? So the approach, the first step is to select a basis B. Okay? And so then the Eigen equation becomes to, so when we take the B coordinate, okay, we can take the B coordinate on both sides, and this is equal to, okay, so the B coordinate of the image is equal to the matrix representation of T relative to the basis V multiplied with the B coordinate of the vector V. And here, this is lambda B. Okay? By linearity of the B coordinate function. Okay, so now, and we let A here, and X here equal to lambda X, where we let A equal to the matrix representation, and the X is just the B coordinate of the unknown vector V. So we turn this Eigen equation into a matrix equation now. All right, so which is called the Eigen equation, okay, of matrix A. Right. In parallel, we call this as the Eigen equation of matrix A. So in here, lambda is unknown. X vector is also unknown. Okay? So let's see. I have to. So in this Eigen equation, V unknown, lambda unknown. Okay? Only T is known. Okay? Now, for this Eigen equation of the matrix representation A, the A of T relative to basis B, this is unknown. This is unknown. This is unknown. Same. But now we have matrix equation. Okay? And we have a lot of tools at hand up to now, okay, to deal with such a matrix. Even though there are a lot of unknown here, only A is known. Okay, so because of this eigen equation for matrix A, so let A be an n times n matrix over F, so can be real or complex. A scalar lambda in F and a non-zero vector U in Fn satisfying the eigen equation A U equal to lambda U. Okay, are called an eigen value of A and an eigen vector of A associated with eigenvalue lambda respectively. Okay, so with just a matrix, so just for the sake of matrix A itself, the matrix can have eigenvalue and eigenvectors. Okay, if they satisfy the eigen equation of A. Sorry, I forgot to put it here. Okay, so to solve the eigen equation of linear operator T on a finite on an n-dimensional vector space, it's equivalent to solve the eigen equation of the matrix representation A of the linear operator T relative to a selective basis B. All right, and as you can see later on, if we can select a good basis such that the matrix representation is diagonal, then the solution will be easy. Okay, it's easy to find the solution, but that we will see that later. Okay, so now the first step, and then we are able to show now we have a theorem 6.1.1, so that A is n by n matrix over F. Okay, a scalar lambda in F is an eigenvalue of A if and only if the determinant of A minus lambda n times is equal to 0. Okay, so the solution, so to solve this eigen equation of matrix A will be split into two steps. First, we will find out possible eigenvalues of A first. Okay, so we will find all possible eigenvalues lambda of A, and then once we first eliminate, so we first turn this unknown into known. Okay, so once this is known, then only X unknown. Okay, that it would be the second step. Okay, and for the first step, we have a theorem. A scalar lambda is an eigenvalue of A if and only if we form a new matrix A minus lambda times the identity matrix its determinant is equal to 0. All right, so we have to show the theorem here. Okay, so a scalar lambda in F is an eigenvalue of A if and only if there exists a non-zero vector U in the Euclidean space such that AU equal to lambda U. Right? So that means that A minus lambda I n times n U equal to a 0 vector. Okay? Any questions for the equivalent statement to saying that a scalar lambda is an eigenvalue of A, then there exists a non-zero vector U, okay, such that this Eigen equation is satisfied. But that says that the kernel of the matrix is not trivial. Okay. Okay? If this is not trivial, so that means that the matrix is not invertible by the inverse matrix theorem in chapter 3, right? So in chapter 3 we know that if the kernel of a matrix is non-trivial, then the matrix is not invertible. Okay? And if a matrix is not invertible, then its determinant is 0. Okay? As we know in chapter 4. Okay? So we prove the theorem here. Okay, so now we are able to use this, and we know we have expansion formula. In principle, you can expand this determinant, and this is will be a polynomial in lambda. So basically, you have to solve a polynomial equation. Okay, right? So basically, it turns out that you have to solve the. That is for a particular matrix A. But how about the T? How about T? We know, so we go back in here, we solve the lambda, right? And we go back, so lambda is eigenvalue, and we go back and find that, okay, there is a lambda satisfying this Eigen equation of the linear operator T. Okay, so we say yes, we can find the eigenvalue of linear operator T. But the question is that if we use different bases, say instead of B, we use a different basis, say C. And so with respect to different bases, the matrix will be different, right? So it will be different. And so the question is that if we use different metric representation, do we have a different possible eigenvalues? Okay. So we have to resolve this puzzle. Okay. Okay, so the puzzle is, so let this matrix be the matrix representation of T relative to another basis C for V. Okay, so now by theorem 5.3.5, these two metric representation are similar. Okay, so we know that these two metric representation are similar, i.e. there is an invertible matrix P, and this P is actually called the transition matrix from B coordinate system to the C coordinate system. We know that. Okay, so that the metric representation are similar. Okay, then we look at the Eigen equation. So the determinant of if we use this metric representation to find the eigenvalue lambda, right? So that we take the determinant, and because of the similarity, this is P, T, B inverse, that's lambda here. But for this case, we can move the P and the P minus P inverse out of here. Why? Because that if we multiply P here and P inverse here, we get the identity again. Okay. So that we have a determinant of P and the determinant of P inverse. But this one is the 1 over the determinant of P. So you can cancel them to be 1, and you get determinant of okay. All right. So in here you see that no matter which basis you use, the metric representation, okay, and to find the determinant, you can see that they will be the same, right? So they will be the same, and So this shows that the determinant of is independent of the basis be chosen for V, so that this determinant, okay, will be denoted as determinant of T minus lambda I, where I is the identity mapping from V to V. Okay? So it's the identity mapping from V to V. All right, so we have several examples to see. Okay, so we will assume, so we let V be a two-dimensional vector space over F, and T is V to V a linear operator, and the B, V1, V2, a basis. Oh, I think I should specify maybe V, a two-dimensional vector space, and B, V1, V2, a basis for V, and T, a linear operator on V. Okay, so I will, this is the general notation I will use in the following examples. Okay, and A would be the matrix representation. Okay, of T relative to B. All right. So now first, okay, A, suppose the matrix representation is this matrix, okay, and so determinant of T minus lambda I, so we compute the determinant. So the determinant is determinant of A minus lambda I 2 by 2. So this is determinant of 2 minus lambda 1, 4 minus 1 minus lambda. Okay, and it's easy, right? So this is lambda square minus lambda minus 6, and by factorization, this is lambda minus 3. lambda plus 2. Okay? Alright, so this determinant is a polynomial of degree, a polynomial in the unknown, in the determinant lambda of degree 2. Alright, so now solving the polynomial equation. So we want to solve the polynomial equation. Okay, so this is our polynomial equation. So this is we have, so the lambda can be 3 r minus 2. Okay, so T has two distinct eigenvalues, 3 and minus 2. All right, so this is the first step. We already know that the eigenvalue of T are 3 or minus 2. All right, so now we want to find the associated eigenvector. So to find the eigenvector associated with eigenvalue lambda equal to 3. So we consider Eigen equation T V equal to 3V, because we know 3 is one of the eigen values. So we first find eigenvectors associated with eigenvalue 3. So we have these eigen equations, and only one unknown, which is just V. Okay, and we check the. So this is going to. Okay, so by taking the b coordinate, we have this one, and so this is equal to ax equal to 3x. Okay, so we know x is just the b coordinate of the unknown eigenvector v, if it exists. Okay, so now we have V is unknown. So x is unknown here. But this is typically, this is what we have learned in chapter 1 at the beginning of the semester. Okay? So we have the ability to solve this matrix equation. Okay, so that is a minus 3 2 by 2 x equal to 0. Okay, so that means that x should be in the kernel of a minus 3 2 by 2. All right, so now our mission is to find the kernel of this matrix. Right? So by elementary So now the A minus 3, which is minus 1, 1, 4 minus 4. Okay. So this matrix. So you plug into 3, and you find this is the by elementary operations here. And from this matrix, you will see that the kernel of this matrix. So you see the unknown x1, x2 should be equal. All right, so you have oh, okay. I'm sorry, I forgot to. Okay, here we will consider our scalar to be real. Okay, to be real. I'm sorry. So we have real eigenvalues, of course. Right. So that this is R here. All right, so kernel is that. So any non-zero vector, okay, x in the kernel, okay, is the B coordinate of an eigen vector V of t associated with eigenvalue lambda equals 3. Of course, such a non-zero vector is an eigenvector of A, right? So x is an eigenvector of A associated with eigenvalue lambda equals 3. So the x itself is just an eigenvector of A, okay? But it's also the B coordinate of an eigenvector V of t. So now, so we selecting x to be B to be 1, 1. Okay, I use U. Maybe I use U here. Okay, so if I select to be 1, 1, then we have, then the eigenvector U will be so which is V2. Okay, so this is a linear combination. We recover back. Okay, so remember V1, V2 is our vectors in the basis B. Okay, so V1, V2 is an eigenvector of T associated with eigenvalue number equals 3. Okay, so we have done. Right now, similarly, all right, the kernel of A minus 2, 2 by 2. Okay, so we have another eigenvalue minus 2, right? And what is that? So this is alpha 1 and minus 4 for alpha in R. Okay. All right. So that's 1 minus 4 x the eigenvector of A, okay, associated with eigenvalue lambda equal to minus 2. And it's also the B coordinate. Okay, the B coordinate of an eigenvector W, which is minus 4, which is V1 minus 4 V2 of T associated with eigenvalue lambda equal to minus 2. All right, so in summary, we have solved basically U is equal to 3U and the TW is equal to minus 2W. So we find eigenvalues 3 and minus 2. And we have corresponding eigenvectors U and eigenvector W. 2, yeah. Oh no, okay. And with these two eigenvectors, we put them together. So we let C to be U and the W. So we put them together, right? And okay. So we claim that C is a basis for V. Okay. So these two eigenvectors form a basis for V. So we claim that. Okay, so consider a linear relation on C. Okay, so alpha U plus beta W equal to 0. So then we plug this into there. We find that we have alpha beta V1 plus alpha minus 4 beta V2 equal to 0. But because V1 and V2 are in here, they form a basis, so V1, V2 form a linearly independent set, so that alpha plus beta equal to 0 and alpha minus 4 beta equal to 0. So this is saying that alpha equal to beta equal to 0. Okay, so C is linearly independent. So it's a linearly independent set of size 2. Now, by theorem 5.2.10, because V is 2-dimensional, and V has, so we know this is, of course, this is contained in V, and V has a linearly independent set of size 2. So this linear independent set should be a basis. So C is a basis for V. So we now find a basis for V And this basis consists of eigenvectors. Okay, they consist of eigenvectors. Okay, so that, oh, time is up, but okay, so now the matrix representation. The matrix representation originally relative to the basis is not diagonal here, right? It's not diagonal. But now the matrix representation relative to this basis, you can see that becomes to okay. What is that? TU is 3U, so this is 3U C. And the TW is minus 2W. So what is that? The first column is 3, 0. Okay? And the second column was 0 minus 2. So it's diagonal. Okay? So which is diagonal? Okay, so relative to this eigenbasis, so we will call this an eigenbasis Y, an eigenbasis, since it consists of eigenvectors. Right? So we have an eigenbasis, and relative to this eigenbasis, the matrix representation is diagonal. And this is what we want. Okay? And so we basically solve our problem. Okay? So even for such a simple example, we need all this information, all the procedures to solve it. Okay? It takes time, but solvable, right? You can solve them in this case. So, okay. All right. So I stop here. Okay, and I continue the subject on Friday. So we take a rest up to 11:20 for quiz.